Hi guys, welcome to the mini lecture on enthalpy. In this mini lecture, we're going to discuss, introduce the concept of enthalpy and see how enthalpy allows us to essentially quantify and understand energy transfer processes in the context of chemical reactions. So to start things off, let's go back and take a look at where we left off with our concept of changes in internal energy. So we introduced this equation. Delta E, changes in internal energy, is equal to Q plus W. So remember, Q and W are both forms of energy transfer. So essentially what this equation is saying is that the total change in internal energy is going to be the sum total of all of the energy transfer processes that are occurring. Whether it's coming in or going out of the system, you add it all up and you're going to get your net change in internal energy. Okay, so remember, Q is our energy transfer, in the form of using these microscopic modes of motion, heat, and we talked about that previously. And W is this work term. Hey, so it turns out that there's two different types of work that we're really going to be caring about in the context of our general chemistry studies, right? One type of work is so-called electrical work, and that's going to be covered in your next semester course in general chemistry when you're talking about electrochemistry. All right, what we're going to care about here for this chapter is so-called mechanical work, okay? And so mechanical work is done anytime a volume changes in the presence of an external pressure. So for example, let's say we have some initial state of the system here, and this system expands, okay? And so this little disk is pushed upwards, and this volume change, denoted delta V here, that occurs, is occurring in the presence of some constant external pressure. So this P here is the external pressure on this system. So when a system expands against this external pressure, it gives rise to a volume change, delta V. The work associated with that process is minus P, that external pressure, times that change in volume. Okay, now with this definition in mind, we can now introduce the definition for enthalpy. So enthalpy is going to be yet another thermodynamic variable, and as I told you, it's going to essentially facilitate or make your life easy when you're discussing energy transfer processes, and it's going to do this by eliminating the need to measure pressure volume work. So here's our definition of enthalpy. Enthalpy is defined as the internal energy plus PV, and we're going to use this variable, we're going to use the letter H, capital H, to denote enthalpy. So enthalpy changes then can be represented by taking our definition and looking at a difference, right? Final minus initial. And if you carry out a little derivation here under constant pressure conditions, delta H equals delta E plus P delta V. Anybody interested in the details of this derivation can go check out a little learning glass video I pulled together on the topic. For the purposes of this exploration here, let's just take this delta H result and explore what kind of information it gives us. So I think it's nice to first look at a comparison between changes in internal energy and changes in enthalpy. And it turns out that for most reactions, these two terms are about the same. So let's look at a couple scenarios. Let's say we've got a reaction that doesn't involve gases. If gases aren't involved, then the change in volume is going to be relatively small, close to zero. So pressure times volume is going to be close to zero, which means this term is going to be close to zero. And so delta E is going to be very close to delta H. So example here, aqueous, aqueous, aqueous in a liquid, no gases are showing up, so this change in volume would be expected to be small, and very close agreement between delta H and delta E for this reaction. Okay. Now you could of course have a chemical reaction equation where you do have gases, but if the number of moles of gases doesn't change, for example, 2 moles on the left, 2 moles on the right, then once again, the change in volume is going to be close to zero, and enthalpy and internal energy changes are going to be roughly the same. Now, even if you do have a scenario where the number of moles of gases does change, it is oftentimes still the case that the energy transfer and heat at constant pressure is going to be much larger than that work, pressure volume work. And so as a result, this delta E being very close to delta H often still holds. Even, for example, in this reaction where you have 3 moles of gas on the reactant side and 2 moles on the product side. But you can keep in mind then, as we predict from the equation, that the larger the difference between the number of moles of gas on the reactant and product side of the equation, the larger the difference between delta E and delta H. Okay, so now let's look at some of the more details of enthalpy. So first off, enthalpy, as it's been defined here on the previous slide, it consists of essentially 3 state functions: pressure, volume, and internal energy. All right, pressure and volume are obviously state functions, and E, as we saw before, the internal energy is a state function. And as a result, H, enthalpy itself, is a state function, which means when we are talking about delta H's changes in internal energies, all we need to do is focus in on what the final and initial states are, look at the difference, and we don't need to be concerned about the pathway, moving between those final initial states. In the context of chemical processes and chemical reactions, the initial state is typically going to be a set of reactants, and the final state will be a set of products that are formed during the course of a chemical reaction. So we can then define a state function, delta H of reaction, as the difference in enthalpy of the products minus that of the reactants, right? And then the sign of this delta H will then tell us whether or not heat is absorbed or released during the course of a chemical reaction. And so we have a couple terms that we use to explore this, right? If you have a process that is giving off heat, okay, we call that an exothermic process, right? Exo means outside, right? So an exothermic process releases heat and results in a decrease in the enthalpy of the system. So the products are going to have a lower enthalpy than the reactants, right? And you've got an overall negative delta H of reaction. So an example here, burning methane and oxygen up here start off as our reactants with a high enthalpy. And during the course of this combustion reaction, you form CO2 and water products which have a lower enthalpy. And so the delta H is the difference between this final and initial state, and it is going to be negative, which means heat is going to be given off to the surroundings. Conversely, if heat is absorbed from the surroundings, then we have what is called an endothermic process. Endothermic process, absorption of heat from the surroundings, is going to result in you must have a higher enthalpy product than reactant. And of course, a delta H of reaction then that's going to be positive. So if you start off down here with a low enthalpy state, and for example, you've got a cup of ice on the table, then that cup of ice on the table is going to absorb heat from the surroundings, increasing the enthalpy of that little cup of ice, and eventually that cup of ice will turn into liquid water. When it's done so, you will have a corresponding enthalpy change that is going to be positive, right? And all of that change in enthalpy corresponds to how much energy was absorbed by that system. All right, so now in a position to take this concept of enthalpy and combine it with what we already know about chemical reaction equations to form what are called thermochemical reaction equations. So a thermochemical reaction equation takes our balanced chemical reaction and includes this enthalpy term. And the given delta H, right, for this enthalpy term for a given thermochemical reaction, it's very important to remember, it refers only to the amounts or number of moles of substance and their states of matter given in this reaction equation. Okay, so these stoichiometric coefficients here, right, and the phases of each one of the reactants and products are both intimately tied to this value of enthalpy change, to this delta H of reaction. So to see what I mean by this, we can actually use the thermochemical reaction equation to construct conversion factors. So if I was reading this chemical reaction equation, I would see that 572 kilojoules of energy is released for every 2 moles of H2O liquid that is decomposed. Okay? In other words, I can form a conversion factor that relates the amount of energy given off to the number of moles of reactant that is used up. And in this way, through the construction of these conversion factors, we can extend what we've already talked about in the context of moles and stoichiometry. We saw how we could use balanced chemical reaction equations to set up these molar ratios to convert between different amounts of any reactant or product. Well, now we can use this delta H term to set up conversion factors such as this that will allow us to convert between the amount of any reactant or product and the energy change associated with that process. So to see an example of this, let's consider the reaction of the decomposition of water once again. So we know that if we decompose 2 molar equivalents of liquid water, we're going to form 2 H2O gas, 2 moles of H2O gas and 1 mole of O2 gas, and the associated enthalpy change is 572 kilojoules. And so in this problem, we are to determine the change in enthalpy associated with the decomposition of 4.00 moles of H2O liquid. So our first step then is to construct a moles to enthalpy conversion factor using this thermochemical reaction equation. So we're starting off with H2O liquid, so we're going to set up a conversion factor that takes us from moles of H2O liquid to the amount of energy given off. Then we can use our initial amount, 4.00 moles of liquid water that we start off with, apply our conversion factor, make sure moles of H2O liquid cancel out, and we can determine the overall enthalpy change associated with this complete conversion of 4 moles of liquid water using our balanced thermochemical reaction equation. As another example, let's consider the formation of SO2. Now, this thermochemical reaction equation illustrated here tells us the amount of the enthalpy change, right, associated with the formation of SO2 gas from the most stable form of each one of its constituent elements, namely sulfur and oxygen. Right? And this is a standard way that we will represent formation processes. We are going to break down a given compound into its individual elements and look at those elements in their most stable configuration. Right? And so in order to do that, and in order to be able to compare 1 mole of a given substance, in this case SO2, to 1 mole of another substance, so we can get these relative comparisons, or just to facilitate the discussion in general, we are going to break a rule that we introduced a couple months ago, right? Namely, when we are balancing chemical reaction equations, I always told you to keep smallest whole number coefficients. In this case, our focus is on this product, the formation and the delta H of formation of a given product, and we want 1 mole of that product. As a result, oftentimes you will have to introduce fractional coefficients in order to ensure that we keep 1 mole of our desired product. Okay, so just keep that in mind. So we're going to break that rule, but that's okay. And it doesn't really change the overarching process. So just as we did in the previous example, if we want to determine the enthalpy change associated with the complete reaction of 3.81 moles of S8, right, then the conversion factor is constructed just as before. And we are going to carry out the conversion by starting off with our given quantity of S8, set up our conversion factor so that moles of S8 cancel out, and then determine your final answer. So according to our calculations here, if we react 3.81 moles of S8, then a negative 9.05 times 10 to the third kilojoules of energy will be released. So the negative means energy is being released. Okay, so there'll be a handful of additional practice problems that you can work through on this topic. For now, we're in a position to go ahead and sum up what we've talked about. We've introduced this concept of enthalpy and enthalpy changes of a reaction. And we've talked about how this enthalpy change is a measure of the energy transfer as heat at constant pressure. And it basically tells us how much energy is being either absorbed or released during the course of a chemical reaction. If energy is being given off, released, we have what is called an exothermic process. If energy is being absorbed, we have an endothermic process. And using this delta H, we could tack it on to what we already know about chemical reactions equations to form thermochemical reaction equations and perform stoichiometric calculations very similar to what we've already talked about. So now that you have a chance now to go work through some stoichiometry of thermochemical reaction equation practice problems, and then after that we are going to move into a series of 3 videos that are going to explore the topic of how is it that we find this delta H value? How do you determine delta H of a reaction? Turns out there's 3 standard ways to do that. We're going to talk about our good old friend calorimetry first as a way to measure delta H of reaction, and then introduce 2 new concepts here, Hess's law and standard enthalpies of reaction.